So the second paper of this session is given by James Teherani, and it's on generation and recombination in tunnel FET devices, and this is a common work between MIT and Sandia National Lab.
Yeah. Hello, everybody. It's my pleasure to be here today, and I guess this is the pessimistic session. We get to tell you things, why we're pessimistic about some things than TFETs. And so I'll continue along that path, and hopefully we'll get some good discussions out of it. So my name is Jamie Teherani. I just started at Columbia, but I'm coming from MIT. So this work was done in collaboration with Winston Churn, Judy Hoyt, and Dimitri Antoniadis at MIT, Sapan Agarwal, who's now at Sandia National Labs, and so funded by the E3S. Okay, so this is a figure adapted from Sebaugh's review paper, latest review paper on tunneling FETs. And so it's showing simulations for N-type TFET. So it's plotting the transfer characteristics, drain current as a function of gate voltage. Now, these dotted lines are the only curves that aren't simulations, and this is for experimental data for a 16 nanometer FinFET process from TSMC. And so this is kind of the benchmark. If we can't beat this with a TFET, there's no point in going to a TFET. And so you see a lot of the simulations do beat that. And that's why we're so excited about TFETs, right? They're showing steep slopes, high currents, and that's what's made us all want to pursue this. But the trouble is, we know that a lot of the experimental results aren't there to support these simulations. So the question is really, what's going on? What is this discrepancy? What can it be due to? And so I'll point out a couple of interesting experimental results. So these are done by 3 different groups. Zhao's at MIT, Dewey's at Intel, and Kim is in Japan. And these are all different devices, all different materials, and these are the transfer characteristics. And you can see that all of these slopes approach 60. 60 is this dashed line, but they don't exceed it. And so this is begging the question, what's limiting us? Is this just a coincidence that we're just approaching 60, or is there something fundamental here? And this is shown even more dramatically in this plot, which is showing the subthreshold swing as a function of drain current for several different devices. These are Dewey's devices. So they do a lot of different techniques. They thin the EOT, making the device better, use a heterojunction, and they just approach the 60 millivolt per decade limit. Interesting. And this is Kim's work. They're showing a lot of different germanium on silicon on insulator substrates, some with strain, some without, with all different processing conditions. And you notice, once again, it's approaching 60, but it doesn't pass it. Okay, so the goal of this work is really to suggest a mechanism not captured by maybe these ideal simulations that could explain the limiting behavior that we see in many experimental devices. So the analysis in this work is really focused on what kind of synonymously called the perpendicular TFET, line TFET, inline TFET, vertical TFET. Here, in this type of device, and the concept here is general, and it can be applied to other designs as well. But in this device, we have a P-type layer and an N-type layer, and by applying a sufficient gate voltage, we induce enough band bending to have vertical tunneling. And we're assuming an ideal device here. We're assuming we have no parasitic corner effects here, no diagonal tunneling, no traps, and this is the device we're looking at. Okay, so we're looking at an even more ideal version of this, perpendicular TFET called the bilayer TFET. And the big thing about the bilayer TFET is that it avoids doping in the channel. And so doping could introduce trap states. And so the way we use this device is, instead of having a P-type and N-type layer, we use gates to form an electrostatic doping to form a P-type layer here and an N-type layer here. So we don't have to introduce any dopants, okay? And this bottom picture shows how the device would be used in operation. You're applying a positive voltage on the top, attracting electrons, a negative voltage on the bottom, attracting holes. And you would turn this device on by applying sufficient voltage on the top such that you get enough band bending to have tunneling. This is what a band diagram looks like. So if we take a vertical cross-section, that's where all the interesting part of the device is occurring, and we look at the band diagram, near the top gate here, we have a well for electrons, and near the bottom gate, we have a hole well. Okay? And so we apply a bias on the top gate, and as we keep applying a larger top gate bias, we keep bending the bands down, and we reduce this energy separation between the electron and hole eigenstates. And so in ideal tunneling, you can't have any tunneling until these states are aligned in energy. You just don't have a state to tunnel into, so your tunneling probability is 0. Okay, so if we were to look at, for an ideal, this ideal tunneling model, if we plot drain current as a function of gate voltage, we'd expect it to be relatively low until right when the bands cross, and then we'd expect a big step. That's the ideal model. But experimentally, we're seeing a lot more gradual. And so it really makes us want to focus on this case just before eigenstate alignment. This is really where we're seeing the largest discrepancy. Because experiment, we're seeing, the current's not decreasing that quickly. And so really, why is this occurring? Well, if we look just before eigenstate alignment, these eigenstates are very, very close together in energy. And so let's just take the case where the separation is around kT, okay? The thermal energy. Well, at kT, we'd expect tons of coupling between these states due to maybe optical transitions, phonon transitions, trap-assisted transitions, and Auger transitions, right? Any thermal effect can create an electron-hole pair between these states. Now, the one I'm particularly interested in is the Auger generation process, because this is fundamental. Auger is not due to a trap state. You can't make the material any better. It's just due inherently to having, so this is the process. You have a hot electron that falls down the conduction band, and that energy is used to knock an electron from the valence band up into the conduction band. So you create an electron-hole pair. Now, this process depends on this energy separation, right? So if this energy separation is larger, you have to have a hotter electron for this effect to occur. And as this energy separation becomes, for instance, kT, then electrons around kT above the band edge can fall down to a lower state and excite a carrier from the valence band up. And the other thing I wanted to point out is this isn't a spatially indirect transition. There's wave function overlap between the hole eigenstate and electron eigenstate. So there's some probability that a hole exists at the same position as like an electron state exists. And so the transition occurs between these eigenstates. Okay, so when we do the math to calculate the net recombination rate for a quantum well, we get this long equation. And a lot of the constants are coming out of doing the density of states, and you have to have energy and momentum conservation, which gives us quite a long expression. But the key things to take out of this are, okay, let me just explain. This is the net recombination rate given in numbers per centimeter squared per second. So the number of carriers that are either recombining if it's positive or generating if it's negative per area per second. And this term here is related to the wave function overlap. This function here, if you're used to seeing Auger rates, this is the driving force of the Auger transition. And this term right here is dependent on the energy separation. This delta E here is the energy separation between the eigenstates. And this is problematic because this term here gives us a thermal dependence on the energy separation. So as we're applying this voltage, we're making the energy separation smaller and smaller, which is what we want because we want to eventually cross the band such that tunneling occurs. But we're also exponentially increasing this net recombination rate through this term. And so to explain this, or kind of give some credibility to it, these are some data for Mercury, Cadmium, Telluride. So this is a 2,6 semiconductor. It's used for infrared detection. And the main dominant factor in the main generation, the the main factor that dominates the lifetime in this material is Auger. And so the reason why I look at this material is it's a small band gap material, right? So 100 millielectron volts. That's kind of order of interest for our low energy devices. And this is a plot of the Auger lifetime as a function of temperature. So because these devices have such a small band gap, they're typically operated at cryogenic temperatures. Otherwise, you have way too much generation, and you just get noise. So they're typically operated around this point of around 77 Kelvin, which is around this point on the scale. Well, if we go to room temperature, we see the Auger rate is dramatically decreasing. So it's at room temperature, it's around a couple of nanoseconds. Okay? So how does this apply to current? Right? So if we look for a related, this is also Mercury and Telluride. This one has a slightly different band gap. And we look at the dark current, which is basically telling us how much generation we have in the dark. Just we have a reverse bias p-n junction. How much current are we generating without detecting anything? And this is a plot as a function of temperature. We can see that the Auger current at room temperature will be really large. Okay? That's why these devices are operated cryogenically. And this is even for a large band gap. I mean, relatively large. As we make the band gap smaller and smaller, as we approach KT, we expect this to go up exponentially. And so the main point is that the turn on due to generation and recombination, if the magnitude of this current, which seems likely that it's high from the last slide, it can overwhelm our ideal tunneling turn on. And so this is something that I really think we need to look at in the field and we need to address. And so that brings me to my summary here. With the small energy separation, generation and recombination mechanisms can couple these two eigenstates. These mechanisms have a thermal dependence, whether you're looking at phonons, traps, or Auger. And they can significantly limit the subthreshold swing, and really future modeling efforts really should consider these effects. Thank you very much.
Thank you. The paper is open for questions.
So I find it easier to visualize Auger recombination, but Auger generation I'm having a little difficulty visualizing. So can you help me visualize that?
Yeah, sure. Okay. So in an Auger generation, an Auger recombination process involves 3 carriers. An Auger generation process involves 1 carrier. Okay. So the 1 carrier here is you have 1 hot electron. 1 hot electron, it just falls down into an empty state in the conduction band, and that energy is used to create an electron-hole pair.
So on the picture on the left, where's my hot electron coming from?
You have some distribution of electrons as a function of energy here due to this eigenstate. So that's the eigenenergy, but it has some distribution because of perpendicular momentum. So you're not only at that energy, you have some parabola.
No, I understand that, but I'm just having a little difficulty visualizing where this is happening. I mean, every semiconductor has a distribution of carriers, a thermal distribution. We don't normally think of the thermal distribution of carriers as creating electron-hole pairs, but maybe it does. But then how does it affect the current to the other triangular
So
quantum
to that
well?
point, we typically don't think of Auger in our normal semiconductors that we use because the effective band gap is large, right? For silicon, it's 1 electron volt, right? And so imagine how hot that carrier would have to be to create an Auger effect. And Auger is also synonymous with impact ionization, if you want to think of it that way. Now, when we're applying these biases to do this density of states overlap switch, we're really kind of changing the effective band gap. And at these really small effective band gaps, these effects can be huge.
Can you illustrate on the left side how that happens? How it gives you current?
Oh, okay, yeah, sure. So you have an electron in the valence band, and you have a hot electron in the conduction band. The hot electron in the conduction band falls, knocking a electron in the valence band up, and then the drain bias sweeps it out. So the drain bias, this is the net driving force. The drain bias perturbs the carrier contribution, this formula here, such that only generation dominates in the scheme that we're interested in.
Hi. Thanks for the presentation. I just have a comment that, despite of this concern, actually I saw a paper, experimental work yesterday, that they saw SS below 16 to the similar structure. Just a comment that, so you use a homojunction in vertical direction, and you need to apply a high voltage to tilt the band.
Yeah.
Isn't it better to use a broken gap?
Yes, I mean, this isn't the bilayer. I'm not proposing that exact structure. That's the ideal modeling structure to explain the concept. But if you have a broken gap heterojunction, you still have this effective band gap, right? And so Auger can still couple those states together, even in a broken band gap. And to the point on the experimental paper that was released yesterday or the day before, it does show. I believe the results that show steeper than 60 millivolts per decade. Now, my current hypothesis on how that could be possible is if you have a tunneling distance modulation effect, that's different than this. This is talking about modulating the spacing. This is the density of states switch concept. If you're modulating a tunneling distance, you're not going to be changing the Auger rate in that. And so if you have a distance modulation device, I could imagine you seeing a steep result. Now, with that said, a lot of work was done at Berkeley to suggest that if you're modulating the tunneling distance, you're not going to see high currents. So it's going to be a low current device. So,
Jamie, a word from the universe of infrared detectors. Well, first of all, people try to design low Auger recombination in infrared detectors made out of 3,5 indium arsenide, gallium antimonide combinations for this very reason. Auger totally dominates as you raise the temperature. And there is a lot of data, if you want to go beyond Mercury Telluride, on relatively new superlattices made out of these 3,5 materials, and there's been several lifetime studies and Auger analysis to look at.
Yeah, that's wonderful. I really think we need to address this. I think it's, in case I didn't make this point in the presentation, what's so scary about this effect is it's fundamental. It's not due to traps. It's not due to something we can improve. And I really think we need to have a handle on this, and that's what I'm trying to set up in this talk.
You can't improve it by advanced structure design.
Yeah, but that's things that we're not maybe thinking about in terms of tunneling FETs, but the IR world has looked at in some detail for quite a long time. So yes, thank you.
One last quick question.
On that sort of band engineering, I see that ratio of effective masses there that with an exponent in front of it. So what do you think the prospects of getting a very heavy conduction band effective mass to limit this Auger recombination?
So I want to take this ratio. If you it's MC over MV. That's if you have like an electron-dominated device. If you have a hole-dominated device, it'll be MV over MC. So you could invert that. So you could, in principle, have a factor of 2 kT, I think. Yeah. You could get 30 millivolts per decade based on this mechanism if you did it right. But there's still some fundamental limit there. That's what unless we do some other tricks to really control Auger in the devices. Okay, thank you very much.
Thank you. Let's thank the speaker again.